Hello and welcome to the Big Data Fundamentals course here at Linux Academy. So let's talk a little bit more about what this course is and who it's for. So what are we going to do in this course? So we're going to look at big data conceptually. Specifically, we're going to look at what big data is and what it isn't. We're going to go over some terminology around the types of data, the V's of big data, machine learning, and data science and analytics. We're going to talk about some architecture problems and their solutions when it comes to big data. So how we ingest data with a data processing pipeline, how we do cluster computing to ask really big questions, how we handle distributed storage to store massive amounts of data, and then how we manage a distributed cluster using cluster management. Then we're going to talk about a couple of the most popular technologies out there right now. So that will be data storage technologies, data analysis technologies, combination storage and analysis technologies. We'll talk about data streaming solution and also NoSQL databases. And then we'll wrap it all up with some use cases. So once we have a good idea of what big data is, how it works, the architecture, the technologies, that sort of thing, the natural next step is to see how we apply that in the real world and how those applications of big data ultimately affect your life. There's a whole host of ways that big data is used today that does have a genuinely large impact on your day-to-day life, whether you realize it or not. So we're going to talk about that in the use cases section. So this course is great for those who are completely new to big data. If you're here out of curiosity to learn a little bit more about what this is, you've heard it talked about before, and you just want some clarification and a high-level overview of what big data is and its fundamentals. And as far as prerequisites go, there really aren't any for this. We're starting from a very, very beginner level with big data topics. It will help you a little bit to have some basic computing knowledge, just to help digest some of the things we talk about in the architecture section. But either way, if you're completely new to everything we talk about here, this course is perfect for you. So without further ado, let's get started.
Hi, my name is Miles, and I'm a course author here at Linux Academy and Cloud Assessments. I have enterprise experience in several facets of IT, ranging from network security, system operations, DevOps, and big data. In my free time, when I'm not renovating some part of my home, I'm binge watching TV shows or playing video games. I'm excited to share some of what I've learned with you, so let's get started.
So if you happen to be new to big data, then you probably heard a lot of buzzwords or jargon being thrown around that talk about data or data analytics, AI, machine learning, all this types of stuff. So what I wanted to do really early on in this course is to first define what big data is. And then in the section immediately after that, in the terminology section here, we're going to talk about some of the other terms you've probably heard of and define those as well. That way you get a differentiation between all these words, the usage of these words in the industry, so that you can navigate all the jargon out there that use these words oftentimes incorrectly. All right, so first let's define what big data is. So I want it to be as concise as possible when defining big data. It's very easy to make a definition very long and therefore very hard to understand. So in this case, I'm defining it with just a single sentence, and we're going to unpack this a little bit. All right, so what makes data big data? A data set is considered big data when it is too big or complex to be stored or analyzed by traditional data systems. All right, so big data is a little bit more than just a lot of data. So you can see I have a few words here colored and bolded. So complex, let's talk about this for a second. So there are different types of data, and we're going to talk about this in the next section, but essentially there's structured data, which is what we're typically used to. It goes in nice rows and columns and in traditional databases. But then there's other types of data that are maybe semi-structured or just completely unstructured. How do we store that data in a way that we can analyze it? And moreover, some of this unstructured data is actually very dense and is huge in terms of volume. So you might have a single item of data that takes up terabytes. Whereas traditional data systems like databases, a single item of data is just a row. It's just a bunch of text. Sometimes you might have, a large glob field in there or something like that. But for the most part, it's pretty small units of data. So big data is a lot of data, but it can also be very complex data. That's not to say that a lot of simple data or a lot of structured data isn't big data. No, that's still big data, but one of the big components to big data that makes it difficult to store and analyze it is the fact that a lot of it, most of it in fact, about 80%, is unstructured. So there's lots of inherent challenges with storing and analyzing this type of data, especially in large volumes. And we're going to go through those challenges and their solutions throughout this course. So traditional data systems here I have bolded. Essentially, that just means databases, your relational databases, which historically is how data has been stored ever since it's been computerized. Until recently, the advent of big data is kind of prompting the use of different types of technologies to handle this different type of data. All right, so let's just clarify here. So big data is a lot of data. Okay, that is part of the definition. But also one of the common characteristics is that the data itself is very complex, which makes it very hard to be stored and analyzed, and is completely incompatible with traditional data systems. As we alluded to in the previous lesson, there are different types of data. So let's go ahead and unpack these different types a little bit further so that we get a better understanding. So we have structured data, semi-structured data, and then unstructured data. So structured data is the data we put in relational databases. It fits into a very nice conformed schema. It all goes in nice rows and columns. Every bit of data in a given table is all the same format, which makes everything easily mapped to predefined fields. So you already know what the data is going to look like, and all the data looks like that all the time. So in terms of digital data, this used to be all there was. Originally, all the data we had digitally was stored in databases. But as technology has progressed over the years and has become more and more part of our lives, we have different types of data now that are being stored digitally that are completely incompatible with traditional databases. So now we have to create these different types of data structures. So next here we have semi-structured data. So this is data that does not reside in a database, but it probably could. Oftentimes, semi-structured data can be massaged and processed in a way that you can get it to fit into a relational database. But a lot of times, particularly with like YAML and JSON, if you have nested arrays of objects in a given unit of data, it becomes very hard to flatten that data down. You typically have to what's called normalize the data. So you have to break it up into individual tables and use foreign keys to relate one row in one table to another row in another table, and it becomes very complicated. So there's a lot of processing that's involved in getting semi-structured data into a relational database format, and sometimes it's not possible at all. So this has prompted the advent of NoSQL databases. So databases that are at their core store semi-structured data, oftentimes in JSON. So Elasticsearch and MongoDB, the two technologies we'll go over in a later section, are both good use cases for NoSQL databases. And they store their documents as JSON. And just like structured data, semi-structured data, again, it's only about 10% of all the data we have. So then we get to the elephant in the room, the reason we have the term big data to begin with, unstructured data. So this is data that does not fit into any kind of logical schema. You can't flatten it. You can't put it in rows and columns. It will not fit in a database. So examples of this in textual format, this would be like documents, like an entire, maybe like a Word document. You have a drive somewhere with hundreds of Word documents or whatever types of documents you have. There's no format to them. There's no schema to them. They all look different. They're all unique. You can't put them in a row and column, and you can't create predefined fields that they're all going to fit into. More data-dense versions of unstructured data would be images and videos, audio files, so music. And then you have things like social media posts or emails, and the list goes on. And you can even have bits of data that have some sort of structure to them, some sort of internal structure to them. But that structure is unique to that individual unit of data, and all the other units have their own structure. So that you can still have some structure to the data itself, but at a macro level, there's not any uniform structure. So unstructured data, unsurprisingly, represents about 80% of all data. And in fact, this number is growing. So the structured and semi-structured segments of data is actually shrinking and unstructured is getting bigger. And it's pretty obvious why. I mean, you just look at the way technology is used in your lives today with social media, with online streaming services. We are storing massive amounts of unstructured data. We're creating massive amounts of unstructured data far quicker than we're creating semi-structured or structured data, which gives a lot of credence to why the big data field is growing so quickly and so rapidly, as it has to answer to all the challenges that we're facing with storing, analyzing, searching, and so on, all this unstructured data. All right, so next let's talk about some of the characteristics of big data. So in this lesson, we're going to talk about the V's. So these are basically just a bunch of V words that help to characterize the data. So just a little bit of history. Originally, back in the early days of big data, there were 3 V's: volume, velocity, and variety. Now, because all 3 of these words happen to start with a V, they became known as the V's of big data. And this kind of spawned an unusual competition in the industry to see who can come up with the most V words to characterize big data. So over the years, this list has grown. So the core 3 were the original, then there was 4, 5, 6, 7. Now, honestly, if you go look online for the V's of big data, you'll probably find lists that have 10 V's in them. Each list will probably be a little bit different. And I've even found a satirical article not that long ago that talked about the 42 V's or something like that of big data. And just it kind of made fun of the whole V thing. So what I did was I took the core 3 V's, which I think are essential to know as they characterize all forms of big data. And then I added some of the other V's. I kind of went up to 7 here that I thought were valuable or useful to know. But the big 3 are still the 3 original here, which is volume, velocity, and variety. So volume, I think it speaks for itself, is the quantity of the data. So the total sum of data you have. So whenever you're designing a big data solution or some infrastructure, you're sizing infrastructure, I mean, one of the first questions you have to ask is, how much data are we talking here? Velocity is how quickly the data is produced or created. So if you're looking at like a data streaming application, or something I built as a data infrastructure engineer was this big operational analytics pipeline. So it took logging and system resource utilization metrics, network events, security events, all these bits of sources of information. And it was all brought into a central Elasticsearch cluster where it was used for troubleshooting, monitoring, asking ad hoc questions, that kind of thing. So when I was building that system, what I had to ask was not just volume, but also the velocity of the data. You'll typically hear this referred to as events per second, or EPS. So in my case, I was seeing between 10 and 25,000 events per second, depending on the time of day or the day of the week. So again, that's another characteristic of velocity here, is it's not always constant. So sometimes the velocity is going to vary. So whenever you're designing or sizing a big data solution, you typically want to consider and size for the maximum velocity you'd expect, and then probably go a little bit further than that. So it's important to know for data that you want to collect how quickly it's being produced, because you want to balance the writing of that data, so the collection and the storage and the indexing, with the reading of that data, which is the searching and analyzing. You don't want the velocity, the speed at which it's being consumed, to impact the speed at which it can be searched and analyzed. You want those two things to function unrestricted. So it's always important to know the velocity, and the velocity can have some impact on volume, but not always. Obviously, if velocity increases, you're creating more volume faster, but typically volume is going to have some sort of data retention policy where you only keep the data until it reaches some size or some age. So you can still maintain some maximum volume and have a variable velocity. So the third characteristic here is variety. So again, going back to my operational analytics pipeline kind of use case scenario, I was getting data from a variety of different sources, from application logs, probably hundreds of different applications, some of them, most of them, in fact, not even logging in the same way. I was getting data from network devices, various different types of network devices that are all in different formats. Web access logs, CPU metrics, memory metrics, disk metrics, all these different types of things. So the variety of my pipeline was actually very, very high. So this speaks to how much data processing has to be done. It speaks to the implementation of the solution. So in my case with Elasticsearch, I had to make sure I segmented the data into different indexes that were optimized for different types of data. So for like the metric data, I had to make sure it was optimized for numerical values. And then for the log data, I had to make sure that it was optimized for full text searching. So I had a lot of different things, a lot of different use cases, a lot of different data types and sources coming in to my central Elasticsearch cluster. So there was a very high variety. So a fair amount of velocity, high variety, and the volume pretty much stayed constant with proper data retention management. But essentially, these are the 3 core V's that you need to ask yourself whenever you're designing, purchasing, implementing, whatever, a big data solution. How much data is it going to be? How quickly is it produced? And how diverse is that data? All right, so we have some extra V's down here. Again, more of these get added every year. I'm sure you can go find lists that are 10 or more. But these are the ones that I found that were actually somewhat useful and worth mentioning. So the first one here, or rather the fourth one here, is veracity. So this is the reliability of the data source. So this is a question that you always need to ask yourself. If the data you're collecting, how reliable is the source? So is it a sensor, or is it some sort of log producer that has internal buffering? So essentially, not how reliable is the data itself, but how reliable is the source. It's always something you want to consider whenever you're using data to help inform critical decision making. All right, so next we have variability. So this actually means a few different things depending on who you ask. So variability can mean basically how inconsistent the data is, or how rather consistent, therefore inconsistent the data is. So this would ask how much of the data present is anomalous. And it's also used in tandem with velocity sometimes. So I mentioned how velocity for my installation fluctuated between 10 and 25,000 events per second. So in that case, the fluctuation or the inconsistency of the velocity could be referred to as variability. In either situation, the variability here is an important question because, again, like I mentioned, if you're using it in terms of velocity, you need to make sure that you're sizing your big data solution to handle that max value, that upper value. And if you're talking about the consistency of the data, then that's going to help inform you how you're going to need to analyze that data. So if you have a lot of anomalous data, then you're probably going to be looking at some kind of machine learning algorithms for statistical anomaly detection. So it's going to help inform you how you're going to search and analyze the data. So next we have visualization. So this is how easily the data can be visualized. So it helps whenever you're designing a big data solution to already know what questions you want to ask the data. For example, if I am indexing some metrics, so let's say some disk metrics, every 5 seconds, I'm going to see how many read-write events there were to a given disk on a server that I'm monitoring, and I'm going to send that 5-second window to some, let's say Elasticsearch. So do I want to send how many read-writes there were in that 5 seconds, or do I want to send how many read-writes there were cumulatively? So ever since I started monitoring it. Basically, do I want to search and analyze individual windows of read-writes, or do I want to search and analyze cumulative sums of read-writes? So for instance, if I had a cumulative sum, I could do a derivative to get a rate of change, and I can see, the read-writes per second over time. And I can see when read-writing is increasing in velocity or decreasing in velocity. So these are types of questions that you need to know up front, or should hopefully know up front. You don't have to. You can always make modifications later. So if you get data into your solution, you start visualizing it, and you're having difficulty visualizing it, then you can always go back either to the data source and make it create the data a little bit differently for you in a way that's easier to visualize, or you can go back to your data processing solution, whatever that might be, and have it mutate the data a little bit differently. That way you can make the data visualizable in the way that you need it to be. And then lastly, we have value. So it is very easy to get carried away with collecting data. Whenever you're designing a big data solution and you can see how useful it is, it's very easy to want to collect all the data from all the things all the time. But at the end of the day, you're faced with a very real situation, and that is big data solutions, big data infrastructure is really expensive. We're talking about dozens, hundreds, maybe even thousands of servers. And depending on the technology you're using, those servers could be commodity hardware, or they could be high-end servers with lots of CPUs, a lot of memory, a lot of really fast storage. So you really need to stop and ask yourself, with every bit of data you collect, is this worth the cost of collecting and storing and analyzing? And sometimes the value of the data, the value that you can extract from the data, doesn't make up for the cost of collecting it in the first place. So value here is kind of the thing that needs to ground you, to not let you get carried away and kind of go crazy. And again, collecting all the data from all the things. You really need to ask yourself and consider what data is most valuable to you. What data do you need to ask the most questions from? Are the answers to those questions valuable? Are they going to inform critical decision making? Are they going to reduce response times to critical incidents? Are they going to answer questions that are otherwise unanswerable? These are the things you need to ask yourself before you start collecting massive quantities of data using very, very expensive solutions. So these are the 7 V's that I really wanted to talk about. Again, you can go look online. You can find plenty more. There's dozens of these out there for you to look at and read about. They do tend to get pretty silly the more you find. So these are the ones that I actually found valuable. Obviously, the core 3 are extremely valuable. They're essential to any design of any big data solution you have. And the extra 4 down here to complete the 7, those are useful things to ask yourself as well, depending on the use case, right? So visualization might not apply to every big data solution. Maybe you're not visualizing anything. Maybe it's just search. Maybe you're just building a search engine or a NoSQL database. But in any case, these are the characteristics I wanted to cover, as I find these to be probably the most valuable ones to consider whenever you're designing or planning to purchase some kind of big data solution. In this video, we're going to talk about another term that you've probably heard pretty frequently, machine learning. So let's get started here. So go to terminology and machine learning. All right, so machine learning is under the umbrella of artificial intelligence. There's a lot of different types of AI out there. We're not going to talk a lot about them because not all of them really have to even do with big data, but machine learning definitely does. So machine learning uses algorithms to analyze data, and then it learns something from the data, and then it can make inferences about the data. So what does that mean? Well, I think the best way to explain this is to just kind of go through a bunch of use cases. So first here I have listed is just to mark email as spam or not spam. So with machine learning, you can create an algorithm and you can essentially teach it what spam looks like. So once you create the algorithm, you want to teach it. So you want to feed it a bunch of spam. Thousands, millions, however many emails you can get your hands on, spam emails. You feed this algorithm all those spam messages, and it will analyze these messages and learn them. Now, when that becomes actually useful is when you implement it into an email client. So an email comes in, and you have this algorithm take a look at it first, and you have it identify whether or not it thinks it's spam, because it has a pretty good idea at this point as to what spam looks like. So it'll either mark it as spam or not spam, and it goes to your junk mail or to your inbox. So that's how the algorithm analyzes the data, it learns from the data, and then it can make decisions based on what it's learned. So you can apply that same technique to categorizing articles, whether they're technology, sports, politics, etc. You can feed an algorithm a whole bunch of technology articles. It'll figure out patterns in word usage and stuff like that, depending on how the algorithm's configured, and it'll be able to identify whether something is a technology article or whether it's a sports article. Another cool use case for machine learning is to determine if text is negative or positive. So this is often referred to as sentiment analysis, and this is used a lot by businesses now with the advent of social media. So for instance, if I'm a business owner, I can take a hashtag. Let's say the hashtag has something to do with my business, or maybe it's just my business name. And I can poll Twitter APIs, for instance, to get all the tweets associated with that hashtag. Then using sentiment analysis, machine learning algorithms, I can determine whether or not those tweets are negative or positive based on word usage, implied tone, all these types of things that are built into the algorithm. And I can get a good idea if there is a positive or negative sentiment about my company. And you can do the same thing with any hashtag or any Twitter handle. You could use it for other social media sites as well that allow you to grab that information through APIs. And you can really gauge the overall attitude around a topic or entity. Another use case you may have seen talked about a lot recently, it's a little bit controversial, is facial recognition. So this is kind of the same way as, marking an email as spam. You feed it a bunch of images of a face. It learns very minute and detailed characteristics of that face, and it can detect it elsewhere. Another use case is anomaly detection. So this is actually one example that is near and dear to my heart. It's something I've done a lot of work with. In particular, I worked with unsupervised anomaly detection, which means that you don't have to teach the algorithms. So with marking an email as spam, for instance, you have to collect a bunch of spam messages and feed that to the algorithm to teach it. Unsupervised algorithms are self-taught. You just feed it a bunch of data and it can figure it out from there. So anomaly detection is a really good use case for self-taught algorithms because it just uses statistical probabilities. So if you're familiar with statistics, if you've ever taken a statistics class before, you'll know that a lot of data tends to form this bell curve shape, with the mean or the average appearing in the middle. And then the further out you get from the mean, are different degrees of standard deviation. So here's 1 degree, out here and here is 2 degrees, and out here and here is 3 degrees of standard deviation. Now, once you've established this bell curve and you've learned what the mean for something is, the statistical probability of a data point falling in further and further degrees of standard deviation decreases. But when you work with anomalies long enough, you tend to realize that a lot of things that look like anomalies sometimes aren't. For instance, here's just a simple graph with some data. And let's assume this data is the number of clients visiting my website over time. So the y-axis here is the number of clients, and this axis here is time. Now you can see here it's pretty steady. There's a little bit of drop in clients. Maybe that's lunchtime or something. And all of a sudden there's this huge spike in visitors to my website. Now you look at this graph and the human brain wants to say, hey, that is an anomaly. It is outside the pattern of the surrounding data. And you may be right. But there's also instances in which this is not an anomaly. So if I look at this entire time interval here and I establish a bell curve, this data point here is going to be pretty anomalous. It's going to be way out on one of these tails, likely past the 3rd degree of standard deviation. But if I look at the time interval right here, right around the data point, and because I'm looking at time, if I look at this exact time the next day, and then the next day, and the next day, or maybe the same day every week, or the same day of every month, you might see this same spike. So let's say I get the spike in clients to my website in the afternoon every Tuesday. Well, in that case, this is not an anomaly. It's a pattern that happens every Tuesday afternoon. Maybe it only happens the 1st of every month, but it does in fact happen at the same time the 1st of every month. So in those instances, it's not actually an anomaly. So anomalies really depend on the context or the perspective in which you look at them. And machine learning algorithms are really, really good at identifying what actually is and is not an anomaly. Because with anomaly detection algorithms, you can configure the bucket size, which is the time interval. So let's say I make a bucket size that is 1 minute, and it's going to analyze the statistical probability of the data points in that 1 minute bucket. And then it's going to move on to the next and the next and the next. And sophisticated algorithms are going to keep track of the time of day of the week, the day of the month, the day of the year. And they will automatically establish this bell curve for each data bucket. And the more data you feed it, the more intelligent it gets. So in my case, with the data I was working with, about 2 to 3 months worth of data made the algorithm extremely accurate. It was able to identify anomalies, and it was able to look at big spikes in data and see them as not anomalies because they happened in a pattern. So this sort of analysis is extremely helpful in all forms of data science and data analytics because it really allows you to find needles in the haystack. And more importantly, it allows you to kind of filter out the false positives. So the things that look like anomalies to the human eye but actually aren't. All right, so next we have fraud detection and prevention. So if you've ever had a transaction blocked, or maybe you got a message from your credit card company asking, hey, did you buy this thing at this location? This is typically going to be created by some sort of machine learning algorithm. So credit card companies and banks are going to use algorithms to identify spending patterns, your unique spending patterns, and then it can find anomalous spending and either alert you or block the transaction altogether if it's anomalous enough. All right, next here we have revenue predictions. This is really good with business intelligence. So using historical data and some present factors about your business, you can use machine learning to predict future revenue. And typically the further out you try to predict, the less accurate or the wider the possible variance is. But it really helps to give a ballpark for companies to kind of shoot for in terms of revenue, because a lot of times you have to financially plan for the year at the beginning of the fiscal year. So knowing what your revenue is going to be at the end of that year is pretty essential to the financial health of your business. Another use case that I've seen recently is success rate measurement. So I've seen success rate measurements particularly used with marketing campaigns. So companies spend millions and millions and millions of dollars on marketing. It's one of the biggest expenses for any company that's selling a product. And being able to actually measure the value or the success rate of a campaign is really, really important because you're spending huge amounts of money on this marketing and you're not entirely sure if you're actually getting a return on that. So by doing sentiment analysis, by analyzing sales, analyzing visits to your website, maybe you're an e-commerce site, many different factors you can use to teach an algorithm historically what is the norm, launch a marketing campaign, and see what changes. So last here we have credit scoring. So machine learning is used heavily in credit scoring, and it's also used in the insurance industry as well in kind of the same manner. Really, I should change this to risk assessment or risk measurement because that's essentially what this algorithm is doing. It's measuring the risk. In this case, credit scoring is measuring the risk of a borrower, particularly the risk to a lender of a borrower. So the algorithms are pretty sophisticated these days and can learn very minute behaviors, spending habits, even life choices, and can pretty accurately assess the risk of a lender lending you money. And the same thing goes for insurance companies when they are underwriting. So underwriting is essentially measuring the risk of insuring a particular individual or a vehicle, and then that ultimately determines your premiums. So using these algorithms, they can access the vast libraries of data, of people, of health habits, health choices, life habits, and life choices. And these algorithms know that if you're a smoker, you're likely to have higher health costs. Or if you're an avid adventurer, you're likely to visit the emergency room more often. But if you're relatively healthy and you go to the gym, a lot of times these health insurance companies will actually reduce your premiums because they know that's going to reduce the risk of health costs. And how do they know what increases or reduces the risks? Well, machine learning. By feeding these algorithms massive amounts of data on health and life and behavior, and then also feeding it information on health cost, it can make correlations from there. So hopefully this helped to kind of pull back the veil a little bit on what machine learning is. A lot of times it's talked about in the industry like it's magic or voodoo, which in some cases it really feels like it is. It's pretty incredible what it's capable of doing. But at the end of the day, these are man-made, human-made algorithms that are just learning something from the data with parameters that we told it to learn from, and then it's making decisions based on what it's learned. And there are no shortage of more use cases that I don't have listed here. These are just kind of the few that are the big ones that are probably most commonly affecting most people's day-to-day lives. So if you found this really interesting, then definitely check more out about it online. There's plenty of resources out there that kind of get more in-depth into machine learning or explain more use cases and how it affects your life because, quite frankly, it's only going to get more prevalent in your day-to-day life. Next, we're going to talk about two topics, and I want to talk about both these topics in the same lesson because I often see them referred to incorrectly in the industry. Some people think they're vastly different, and some people think they're almost the same. So hopefully we can pull back the veil a little bit and help explain some of the differences and the similarities between data analytics and data science. So data analytics is processing and analyzing data sets to model and communicate answers to specific questions with actionable data. So here we have data, we need to process it, we need to clean it up, parse it. We want to analyze that data. So analyzing data basically means asking it questions. Modeling that data is basically converting it to visualizations. Visualizations help you to communicate that data much better to people who aren't data analysts. And we do all this so that we can answer very specific questions. So the skills required to do this is a good understanding of statistics. You want to have a general understanding of computer science. The ability to program is useful. R in particular is a really heavily used programming language to do data analysis and visualization. And a good understanding of AI. So being able to use machine learning and deep learning, etc. algorithms. You don't necessarily have to understand fundamentally how they work and be able to create them, but you should be able to use them. So ultimately, the goals for data analysis is to provide solutions to known unknowns. So I have a question, I have a known question that I don't know the answer to. So it's a known unknown. And data analysis seeks to answer those specific known unknowns, those specific questions. All right, so let's take a look at data science and kind of compare and contrast as we go with data analytics. So data science is a multidisciplinary field, which means there's many disciplines involved. We'll get more into that specializes in exposing insights from large data sets. So multidisciplinary here is because you need to be essentially a scientist. We're going to use the scientific method. You need to be very adept with mathematics. It's pretty typical for a data scientist to have a PhD in mathematics. You really need to have a good understanding of computer science because you have to understand algorithms and data structures and how to program, because you need to use these advanced mathematics and computer science skills when you're creating AI. So you're creating machine learning, you're creating deep learning, you're creating these algorithms that are being used in data analytics. So there's a heavy amount of computer science and mathematical principles that have to be applied when you're creating those algorithms. And then lastly, again, a heavily used skill is data analysis. So if you're creating stuff that's to be used for data analysis, then you have to be able to do data analysis. All right, so how do the goals differ a little bit with data science and data analytics? So the goal for data science is to understand phenomena. So in this case, phenomena are unknown unknowns. So with data analytics, we talked about known unknowns. I know the question, I don't know the answer. How do I answer this question with data? With data science, there are unknown unknowns, which means I don't even know what questions to ask. So data science will actually identify questions that we didn't know to ask in the first place. So these are unknown unknowns. And obviously, once we identify them, then they become known unknowns, and then we can answer them with data analytics. And then lastly, data scientists find better ways to analyze data, which ties back to the skill set of artificial intelligence. So being able to not just use, but to actually create these machine learning algorithms, which again requires a lot of mathematics, a lot of computer science, and then applying those to data requires the scientific method and data analysis. So you can see here that data analytics and data science, they're not the same thing, but they're not super different either. They're really two sides of the same coin. Data analytics is very tactile. You can actually see and visualize what is happening when you perform data analytics. It's very easy to understand what's going on there. I have a question. How do I answer it? Data science seems to be a little bit more obscure in definition to a lot of people that I see out in the industry, but ultimately it's what makes data analytics possible and powerful. So hopefully this lesson helped to clarify the differences between these two, but more importantly, the similarities and how closely coupled these two concepts are. So this lesson is the first of this section where we're going to be talking about big data architecture. So we're going to go over some of the themes that you're going to be seeing in a lot of big data architecture and data pipelines. Now, everything we talk about isn't going to exactly apply to every solution. There's going to be a little bit of variation, but overall, this is more or less what most architecture in big data is going to look like. So for this lesson, we'll go to architecture, and the first one here is data ingestion. So when it comes to big data infrastructure, one of the hardest things to figure out a lot of times is collecting all the data. And there's a number of different ways you can collect the data. So you can either push the data from the device that's creating it to your data pipeline, or you can use what's called a polling proxy or some kind of proxy that basically polls an endpoint on some interval for data, and it either responds or it doesn't. Now, when designing your architecture, I will mention that push is always better than polling. In some instances, you have to poll. You can't help it. But push is always going to be better. It's real time. It's less resource intensive. For instance, with polling, if there's nothing to say and you're polling every 5 seconds, there's nothing to actually get. But once every 10 seconds or even a minute, you're using a lot of resources to go back and forth and back and forth. And it's kind of like when you're taking a long road trip. It's like, are we there yet? No. Are we there yet? No. Polling is a little bit wasteful, but sometimes it's what you have to do if the endpoint in question doesn't have a mechanism to push the data. So let's talk about some of these endpoints, and then we'll talk about the rest of this pipeline here. So endpoints can vary. So I have some of them listed here. There's plenty more that you can think of, but let's just start over here. So end user devices, which is what we have up here at the top. So I have this connected using polling, but servers and end user devices are more than capable of pushing to a queue, pushing to a pipeline. I just have this to illustrate that some of your endpoints might be polling, But anyway, so end user devices, so IoT devices. It's important to remember sometimes when people use the word IoT that we're talking about a massive umbrella of devices. We're talking about all of the smart devices that are currently existing and are being created every week. I feel like there's a new smart device out there every week. It's from home automation with security systems, camera systems, smoke alarms, thermostats. You have scientific equipment, so scientific measuring equipment and scientific sensors, geological sensors, weather sensors, whatever it is that is connected to the internet that's not a personal computer or a server. So there's a huge, huge umbrella here whenever we say IoT devices. And they're one of the biggest producers of data. So if you think historically about data, originally it was all human-entered data. So humans created the data, they put them into databases, traditional databases. And then now, as more technology has advanced, more and more data is created automatically without humans. And IoT is playing a big role in that data creation. So then we have some other personal devices, so phones, computers, and point-of-sale registers, or POS registers. So these are all devices that are creating logs, they're creating some sort of metric data, sales data, usage data. Again, phones has geographical data and usage data, and just general lifestyle data. And then IoT devices we already kind of covered. These things are creating lots and lots of data. And there are plenty of use cases in which you want to collect the data from these devices. All right, so next we have servers. So the backbone of all of the services and applications we use with our end user devices are servers. So some common things we can collect from servers would be web server access logs. So the access logs for a website, application server logs. So typically when you access a website, it's going to go through, web server, hit an application server, do some logic and come back to the client. So application server logs are pretty useful. It's also nice to correlate these two, which is a little bit more advanced, but correlating the life of a request through a web server log, then an application log. Maybe it's a microservice, so it's hitting a bunch of different microservices and a microservice gateway. Needless to say, when you request something from an application or a website, it's often touching a lot of different either web servers or application servers and tracking that single request through how all of these individual requests are related can be pretty useful. Then we have system logs, so the actual system itself that whatever your service is running resides on. And then we actually have the system resource metrics themselves. So CPU, memory, disk, network, all that kind of stuff. These are all very useful things to collect for operational analytics, log aggregation. This allows you to troubleshoot incidents very, very quickly, allows you to identify anomalies to help prevent incidents before they happen, and in general, just increase uptime of services. So we have some cloud devices that we can collect from. So we can get cloud server logs, network metrics, resource utilization, so similar to the server stuff up here, and then cloud application data as well. So then we have the thing that connects all of these devices together, which would be network devices. So we have firewalls, so we get logs based on what is allowed, what's denied, that sort of thing. Wireless routers get information on all the connected clients and throughput. Then we have IPS and IDS systems. So these are intrusion prevention systems and intrusion detection systems. So these are devices that have some filters and some logic inside of them to determine whether or not there is malicious activity or malicious traffic. And the IPSs will actually block that traffic and IDSs will just alert on that traffic. So this is extremely useful whenever you have a SIM environment to collect this data to analyze security risks and active security activity. And then we got routers and switches, so the things that basically send all the requests to where they're supposed to go. So we touched a little bit about applications over here with application server logs, but applications themselves have a little bit more than just logs, which is the first bullet here. But there's also status information. So monitoring applications sometimes is a status page or something you can use. Often this is going to be a polling mechanism unless the application itself can report its status using heartbeats. Then we also have usage metrics at the application level and resource metrics. So maybe it's a Java application. You want to get resource metrics on the JVM heap and how often it's garbage collecting, full garbage collections versus short collections, how much of the heap is used, that sort of thing. Maybe it has a database backend. You want to see what SQL requests it's sending to that database. All this useful information to help troubleshoot, monitor, and also to make decisions for optimization. And the last thing I have here, which again, you could probably think of some more. These are just kind of the big things that I can think of off the top of my head. Storage systems. So this is kind of data at rest. A lot of these things here are data in motion. Storage systems is data at rest, so we can get status information on storage systems. We can get usage and capacity metrics, logs, and then we can also just get the information from these storage systems themselves and just put them into a data storage and analytics tool. All right, so this is just an example of some of the devices and data sources. So you're going to get these into your pipeline either through polling or pushing, like we talked about. It's very common to use a queue as basically the first step in your pipeline. So obviously if you have polling proxy, then the queue, and then everything else would just push to the queue. So this is really great for managing back pressure. So back pressure is when your data processor or your storage and analytics tool, something is slowing down up here. Either something has failed or there's just a big burst of data, and this can't keep up with the events per second being generated by all of these devices. So when that happens, you have a generation speed, an EPS speed, that is faster than the processing speed. So that is when we have back pressure. So the queue is a great place to kind of buffer up that data, let this queue grow and grow and grow, and hopefully the back pressure is relieved at some point, and then it can catch up from that queue. If you didn't have a queue, then you would basically just be dropping data. So if you're just sending stuff straight to a data processor and it can't keep up, oftentimes the mechanism it has to use is just drop, and you're just losing data. It also allows you to take any of these systems down. Maybe if you have to take them full down for service or maintenance or whatever, you have a queue here that can keep collecting that data. So then when these services come back up, you can pick up right where you left off and catch up to live data. So queues are really important for maintaining high availability and data integrity for your data pipelines. And in fact, in the next section, in the technology section here, we're going to talk about a service that can be used as a queue called Kafka, which I have used personally in production as a queue, and it works very, very well. All right, so we have all the data in this central place in this queue, and then we can basically collect it. That's the other really, really good thing about the queue, is that you can have multiple things collect the data. So maybe you have one data processor, maybe you have something else, maybe you have applications that want to collect this data. You can have multiple things all collect from this single queue with their own offsets so they can share the data independently, rather than having all of your devices send to multiple locations. You just have them all send to one, and then from there you can disperse the information as needed. So in this case, we're going to disperse this information to a data processor. So this is where you're going to basically process the data. You're going to clean it, you're going to parse it, you can format it, you can enrich it, so you can add information to the data here. So for instance, for web server access logs. So this is going to get to our data processor, and maybe we have a client IP address. So we can use a GeoIP database at this point to look up that IP address and get some geographical information. What country are they from? Or what city are they from? What's their postcode? And then we can add that to the event and then continue it on. So it's not just parsing and cleaning, but it's also enriching data as well. And there's various ways you can enrich the data here. This is going to be a very CPU intensive step. Oftentimes, if you get really large bursts of information, this is where back pressure might begin. But once the data is processed, cleaned, and enriched, we can send it on to our data storage and analytics tool. Now, sometimes this is going to be multiple tools. You might have a separate storage tool and then a separate analytics tool that reads from the storage tool. In this case, I just have it represented as one. But again, this is just a high-level overview of what most pipelines are going to somewhat look like. So once you get the data into your data storage and analytics tool, and assuming you have a well-architected tool here, so the velocity of the data coming in, the events per second, is not harmfully impacting the search velocity that you want to search this data at, and you have enough storage, the storage is fast enough to keep up with the events per second, so we don't have back pressure at the tool, all these things that factor in, then you can start asking your data some questions. Okay, so just a quick review. So we have data from all over the place. It can be anywhere. It's very diverse data. It has high variability and various mechanisms for collecting it. Sometimes we're going to poll, sometimes we're going to push, but ultimately the end goal is to hopefully get all the data into a queue. Once all the data is in the queue, now we have a central location to basically subscribe to that data. So in this case, we have a data processor that's going to subscribe to that data. It's going to consume it, parse it, enrich it, and then pass it on to our data storage and analytics tool. This is going to store the data. It's going to index it for fast search. And then we can use analytics and visualization to ask the data questions, and then use those answers to support critical decision making. In this lesson, we're going to talk about a problem that has constantly plagued data infrastructure in the past, and big data has found a novel solution to it. So let's go ahead to architecture, and let's go to parallel computing. So let's just compare and contrast non-parallel and parallel computing, what the issues are with this as we deal with big data. So traditionally, or historically rather, traditional databases have been non-parallel, which means the computation, the execution, the task, the job, whatever it is, whatever you want to call it, whenever you do something with a database, whether you're putting data in, changing existing data, or reading the data that's already there, those tasks are not parallel. They have to be performed on a single instance of the database, on a single machine. Even if you had a traditional database that was clustered, so it had the data kind of spread out on multiple compute nodes, or you have an active-passive setup. Active-active is pretty uncommon, but it is possible with some database systems. You're still very limited to how you can split that task up, that job, and spread it out across multiple nodes. Historically, with these types of systems, in order to upgrade, so if the demand, if the things you're asking the data or the executions you're trying to perform are too great for the hardware, the way you would improve the hardware is to replace it out with the old and with a new, bigger machine. Something that's more powerful that can actually handle what you're asking from it. Now, when we start dealing with big data, this becomes a very unsustainable process. So big data tackles this with parallel computing, which allows you to scale horizontally. So you have a task, you have a question, whatever it is, a job, and that goes to some sort of master node or coordination node, some sort of kind of cluster management node. And then that question gets routed or dispersed to multiple nodes. Each node does its job. It comes back to the master node or coordinating node. All the individual nodes' reports kind of get merged into one and then sent back to the client. By using this sort of architecture, we can near infinitely scale the compute ability of a big data solution by adding more and more nodes and breaking up these parallel tasks more and more. So now when you run into an issue where your infrastructure can't handle the demand, it's not powerful enough, you have some options. You can just add some more nodes that will increase the overall compute, and you're not actually replacing anything. Or if your nodes are pretty old, you can demote them to warm nodes or cold nodes, and I'll talk about what that means in a second, and buy new nodes that you can call them the hot nodes. So with data infrastructure, particularly time series data, you typically have hot, warm, and cold data. So hot data would be, if it's time series, it'd be the most recent data, the data you're looking at as it's coming in. You're accessing it all the time, you're searching it all the time, you're visualizing it. Maybe you have a live feed dashboard or something. It's very hot data. It's very active, and you need to use it a lot. Warm data, again, for like if it's time series, might be a week's old data, and then cold data would be anything older than like a month. And the age of where these fall into the categories entirely differs on your data and your use cases for it, but these are just examples. So let's say you have a bunch of data nodes and you've expanded and you've expanded and you've added more and more nodes to them. They're no longer able to keep up with the requests you're sending them. So now instead of just replacing all these nodes, you can just demote them to, so let's say warm nodes, data that's accessed less frequently, less often, and then buy some new hot nodes. And you can continue recycling your nodes through this process until eventually they're out of warranty or no longer supported or what have you, and then you can replace them all together. So by scaling horizontally with parallel computing, it solves two problems. It solves the problem of quickly scaling and cheaply scaling your cluster to meet the demand. And then with different clusters of nodes all in the same solution, using hot, warm, cold architecture, you can continue to recycle those nodes and get more value for your money spent. So it's important to clarify here as well with the parallel configuration here, we have some sort of coordinating node or master node. The reason we have that is, let's think about a single node here. If we had just a data node or we had the non-parallel over here with the traditional database, these nodes have multiple CPUs. Sometimes for servers, they can have, over 100 CPUs. Now the node itself, the kernel, is actually handling all the scheduling and the logic behind what process gets how many CPU cycles and when. So the individual node is coordinating its own threads and its own processes. So there is some parallel action going on within the individual node. So with big data, we're basically just taking that same architecture and we're scaling it back. So we're coming back to, now let's not just parallelize the individual nodes, but let's parallelize into a cluster and have a bunch of nodes. So it's multi-level parallelization basically. So once you do that, once you take a bunch of different servers and you have them all basically behave as if they're part of the same entity or are the same entity, you need that thing that, what the kernel does on each individual host, you need that outside to manage the whole cluster of nodes. So you need that thing to handle the scheduling. It needs to know where the data is, where to send requests. When it gets responses, how does it merge them or mutate them before sending back to the client, handling all the client connections, and just routing everything to and from the various data nodes in the client. So it's very, very typical when you're working with big data infrastructure to have some kind of coordination node or master node. And then you have data nodes or worker nodes or whatever they might be called that actually do all the heavy lifting. So hopefully this helped to illuminate how big data uses parallel computing to both solve the scaling and the reusability of expensive hardware problem. So some of the same issues that plague data infrastructure when it comes to computing and using parallel computing also plague it when it comes to storage. So let's take a look at storage architecture here. So one of the biggest things with big data is using distributed storage. There really is no other way to actually properly store and work with big data without distributing it. There is no host, there is no drive big enough to store big data by itself. So monolithic storage is something we see a lot with traditional databases. That's not to say some of them don't support some form of distributed storage, but more often than not, they're monolithic storage. You have a drive or you have a RAID of drives on an active node, and then each time you write to this node, it is synchronized to a passive node. So these two hosts ultimately have a copy of the data. So here's the primary copy 1, and here's a replica of 1 or R1. Now, with these types of configurations, typically what you have is all write operations have to go to the active node, and then read operations prefer the active node, but let's say this is busy, it could also go to the passive node. So kind of similar to the processing problem with monolithic storage, upgrading is out with the old and with the new. You have to buy bigger, faster drives to handle a bigger and faster demand. And you just have to keep cycling through your hardware as your demand grows. So again, completely unsustainable with big data solutions. So with big data, we use distributed storage. So again, we have multiple nodes. They are managed by some form of master or coordinating node. I don't have them illustrated here, but there is some sort of management tier going on between these nodes. But ultimately, the data is broken up. So here we have one chunk of data. It's all on the active node, and it's replicated to the passive node. With distributed storage, you break your data up into multiple chunks. So here we have 1, 2, 3 chunks of data that comprise our total data set. And then we can replicate each chunk individually. So notice the replica for chunk 1 is on node 2 and on 3. So we actually have 2 degrees of replication here, which of course is configurable. You can have 1 or up to the number of nodes you have minus 1 levels of replication, because you don't want a replica of chunk 1 on node 1. Because if node 1 goes down or something happens to it, you lose both your primary and your replica of that chunk. It kind of defeats the purpose of having a replica to begin with. It's for redundancy and high availability. So if node 1 were to fail here, we have R1 here gets promoted, or R1 here gets promoted to being a primary. So now when write operations come in to chunk 1, those operations are replicated to R1 here and R1 here. Same with chunks 2 and chunks 3 to their replicas as well. And then read operations again can happen on chunk 1 here, it can happen on chunk 1 here, or it can happen on chunk 1 here. So not only are you distributing the storage and allowing for horizontal scalability, but just by adding more and more nodes and splitting your data into smaller chunks, you're also increasing search throughput, because now if this node is busy, I can search the same data on this node, even though it's from a replica, it's not a primary. And the more nodes I have, the more replication I can use if I want to increase the fault tolerance of the cluster. And then I can just keep scaling these nodes, adding more and more to the cluster as my data grows. And just like the parallel computing example, we can also use hot, warm, cold architecture here as well. So we can put our hot data on our fastest storage nodes. Maybe they have NVMe hard drives. They're lightning quick, but very expensive. But we don't want data that we don't use often or access often on those really expensive nodes. We can put those on less expensive nodes. Maybe they have spinning disks or slower SSDs. Because we don't need them to be fast, we're not going to access that data very often. So it allows you to be very selective with where you spend the money and kind of spread that money out and spend more of it on your hot data and less of it on your cold data. And allows you to recycle the nodes through those tiers as well. So as your hot nodes get older, maybe you can demote them to warm nodes, buy new hot nodes, and continue that through until by the time they're done with their cold node lifecycle, they're going to be out of warranty and no longer supported. And then you can individually scale each of those tiers as you need to. So maybe you want to increase data retention, so you want to increase the number of cold nodes you have. Well, now you can go out and buy a whole bunch of not so expensive nodes because they're cold nodes, add them to the cluster, and boom, there you go. You have a whole bunch of extra storage, cheaper storage, and now you can retain data longer. Whereas if you had monolithic storage, you're replacing the entire thing. So distributed storage allows us to kind of spread this data out. It's now faster to write this data because instead of writing a megabyte to one node and then syncing it to this node, in this case, I have 3 nodes, so I'm writing 1/3 of a megabyte to each node and then replicating it in the background. So we're increasing the speed at which we can write this data. We're increasing the search throughput of the data, so how many individual persons or clients can search the same data at the same time because we have the data on multiple nodes. We have more fault tolerance because we can replicate this data as many times as we need to up to the number of nodes we have -1, which is going to increase our availability and uptime. And then again, we're making it easy to scale to your data demands and to recycle your nodes through different tiers, hot, warm, cold, to get more value for the money you spend. All right, so the last thing I want to discuss in terms of architecture with big data is something we've alluded to already, and that's the master and coordination nodes, or what we're going to refer to as cluster management. So here's kind of a high-level illustration of a cluster. So we have a bunch of some kind of node here, so data nodes or worker nodes, whatever they might be called. These are essentially the data storage nodes doing all the heavy lifting. And then we have these master eligible nodes or coordination nodes. Various technologies will have various names for these things, but the overall theme here is generally the same. Something I didn't mention earlier is that it's also a good idea to cluster your master nodes. So in the same way we cluster our data nodes for high availability and redundancy, we would like to cluster our master nodes so that if this master, the currently elected master node, fails, there's another node here that can pick up where it left off. That way you don't have a single point of failure, aka the master node, in any given cluster. All right, so now that we have a good idea of how parallel computing and distributed storage works, let's talk a little bit more about the purpose of these master nodes. So the master node is going to deal with creating and deleting data chunks. It's going to keep track of each node in the cluster. So if I decide to scale my data storage nodes, this data storage node is going to have to reach out to my master and ask to join the cluster. The master can then either add it or not add it, and then keep track of it. So it's going to keep track of disk usage, CPU usage, what data it has, whether the data is a replica, and ultimately it's going to try to balance the load and the storage across all of these storage nodes. So it's going to decide where to allocate chunks, kind of like what I just said. If any one of these nodes, let's say one of these chunks on this node here gets really, really big, it might opt to take some of the other chunks on this node and send them to other nodes to help balance out the cluster. So it's going to promote replica chunks and rebalancing the cluster during node failure. So if this node goes down, it's going to immediately find the replica for each chunk in this node, promote those, and then it's going to start re-replicating those chunks because now we're missing a replica of several chunks. So the master node is going to say, hey, we're not at the desired level of replication for the chunks that were on this node. This node went away, so let's start re-replicating those chunks. Meanwhile, the replicas that we already had are up and running and we haven't skipped a beat. It's also going to route search requests to the appropriate nodes. So if I'm a client up here and I request something from this cluster, I'm asking the data a question, it's going to go to the master node. The master node is going to decide where that data is. Let's say that data is on 3 of these nodes. It's going to ask each of those 3 nodes. They're going to respond back to the master. It's going to merge it and send it back to the client, which is the last one here, merging search responses. So let's go back to parallel computing for a second here and talk about that a little bit more. So here we have the question, right? So we have what or who are the top 10 X by Y. So let's say who are the top 10 clients by number of requests. So that's a question we can ask our web access data. So here I ask that question to a non-parallel configuration here. It has to churn through all the data, has to figure out the answer, and it has to come back. So let's say it takes 5 seconds for it to do that. Now over here, my data is dispersed across all of my data nodes because we have distributed storage. So over here, I have the same chunk of data distributed across 5 nodes. So now I ask the question to the master node, hey, who are the top 10 clients by number of requests? The master node is then going to send that question to all 5 of these data nodes, assuming they all 5 have a piece of that data. Each data node is going to ask itself that question. Who are the top 10 clients by number of requests? And they're all going to return their top 10 back to the master node. Then we have what's called a merge process. So that's what we talk about here, merging search responses. So the master node is going to essentially have the top 50 because it's the top 10 from each node. So it's going to sort that list, get the top 10, and then send that back to the client. So there's a small amount of overhead right here, but it's very, very quick because it's already sorted coming from each of these data nodes. So let's assume that searching data the amount of time it takes to search data is linear to the amount of data there is. That's not necessarily true, but for the sake of this argument, let's say that it is. Then that means that we can perform this search request in about 1 second. Because over here, it's a 5-second search request to this non-parallel kind of monolithic storage structure. And over here, we're breaking that request up. We're adding a tiny bit of overhead to it, so maybe it's slightly more than a second, and then we're sending it back to the client. So those are some of the key purposes here of a master node. The purposes here will also vary depending on the technology. We're going to talk about several technologies in the next section and kind of get a better idea of how each technology utilizes the master and storage structure, distributed storage, and parallel computing. So again, purposes can vary, but these are typically the things that you're going to see more or less across every technology. So some key points about master nodes that is useful to keep in mind. They are typically smaller than the nodes that contain data. So they're typically smaller than these storage nodes. Keep in mind these storage nodes have to have really fast and often a lot of storage and enough CPUs to search and analyze that data rather quickly. Master nodes, while they do have a lot of purpose here, a lot of jobs and roles to perform, they have a lot to keep track of. In comparison to storage nodes, they're not that resource intensive, so they're typically going to be a lot smaller and therefore less expensive. But just because they're smaller doesn't mean they're not important. In fact, I would argue they are the most important node in any distributed system. You can have 1,000 really great, really fast, really expensive data storage nodes that have petabytes of data on them. They are completely useless unless you have some sort of coordination or master node. Because without that, they can't form that single entity of which you can write to and read from. So because of that, redundancy here is very important. In the same way that redundancy is important in storage nodes, because we don't want to lose data, so we want to replicate the data across so that if a node goes down or loses its data, drives get corrupted, we still have replicas elsewhere. Data loss is a very, very bad thing. But again, this cluster is completely pointless without a master node. So we want to replicate the master nodes as well. Now, not every technology is actually going to be clusterable at the master level. Some of the older big data technologies, to be specific, HDFS, doesn't have a truly highly available name node cluster. Name node is their version of the master node. So HDFS technically does have a form of a single point of failure. They have a secondary name node, but it doesn't quite work in the same way as a fully redundant master node cluster. But again, that only really applies to the older big data technologies. All the modern big data technologies are going to have a clusterable master tier. And it's important to mention here that the master nodes, in particular the entire cluster, is going to perform best with very low latency. Now, when I say very low latency, I mean very, very low latency. Distributed systems like as small latency as possible. If you can get your latency less than a millisecond, if you're somewhere in the microsecond range of latency between hosts, then your cluster is going to perform best. Keep in mind, everything your cluster does has to be shared with the rest of the cluster. So if I write a file to node 1, then the master has to basically tell node 1 to write this file, and then it has to tell some other node to replicate that file, and then all the other nodes have to keep track of each other, and the master nodes keep track of where all the data is. So if the communications between the nodes is slow in any way, that becomes the weakest link to the overall cluster. You can have the fastest storage, the fastest CPUs possible, but if you have high network latency, then everything is very sluggish, and you'll never be able to fully saturate all those expensive resources you bought. So you definitely don't just want to focus on the nodes and their speed and performance. You really do want to focus on the network as well, and very low latency is best. Okay, so hopefully this helped to shine a brighter light on just what a master node or a coordinating node does, and why it's the single most important node in your distributed system. So now we have a good understanding of the terminology and the architecture of big data systems. Let's go ahead and look at some popular technologies. So these aren't obviously all the technologies out there. There are dozens and dozens and dozens of them. These are just some of the big ones that you're going to see more often than the others. All right, so up first we have kind of the elephant in the room, quite literally, HDFS. So Hadoop is pretty unanimous with big data. They're one of the first major players in terms of big data technologies in the market, and has been very, very popular early on and even still today. Even as a lot of newer technologies, more modern technologies with more features and fault tolerance have come out, Hadoop is still kind of held on to a fair share of the market. So let's just take a quick look at HDFS here, get an idea of what it is, how it's used, and how it works. So HDFS is the Hadoop distributed file system. So it's a distributed file system designed to run on commodity hardware. Now, there's nothing stopping you from running it on really fast hardware. In fact, some people do, but it was designed from the onset to be able to run on commodity hardware, which is kind of mid-tier or low-tier hosts. So this is kind of going back to the monolithic historical traditional database structure of these really, really big, expensive machines that have to handle the demand that you're giving them. And then you can't really scale them except to replace them out with the old and with the new. So with big data, we really needed a good way to distribute that data across cheaper machines. So that's where Hadoop has come in. And there have actually been quite a few companies who have actually built Hadoop clusters with multiple thousands of nodes. So HDFS is definitely very scalable and cheaply scalable because it can be run on cheaper hardware. So the second bullet point here should have a little asterisk at the end of it, but I'll explain. So it is highly fault tolerant, but at the data level. So we'll talk about in a minute how it works to show how it's fault tolerant. It should be mentioned that the name node level, the name node is what they call the master node or the coordinating node, is not very fault tolerant. It's kind of something that's plagued HDFS ever since its onset. And even though it is open source, it doesn't seem anyone has really stepped up to really address this issue. There are some third-party solutions to it, but nothing really core to HDFS that really solves the name node single point of failure problem. However, the data nodes and your data itself is all very, very fault tolerant. So as long as you're using some kind of queue in your pipeline and you have proper replication on your data nodes, worst case scenario, your Hadoop cluster goes down because of the name node issue, but you're not going to lose any data as long as you're buffering it beforehand and it's replicated within the cluster. Once you fix the name node, you get it back up and you're back up and running. No data loss, which is the big thing. So it's designed for very large data sets. So as I mentioned, some companies have already used this with thousands of nodes. So you can imagine if you had, 2,000-3,000 nodes in your Hadoop cluster, you can handle some pretty big data sets. And obviously, in order to do that, it is very much horizontally scalable. That is the ultimate premise of Hadoop. The fact that it can run on commodity hardware is to the fact that it is horizontally scalable. And lastly here, it's worth mentioning it is an open source project, so you can contribute to it if you would like to through the Apache Foundation. All right, so what is it used for? So it's used for storing large amounts of data, structured or unstructured, and it ultimately provides a storage framework for data analysis tools like MapReduce to operate on. So HDFS is not a data analysis tool. You're not going to use this to ask your data questions and visualize data. You're going to use this to store your data. And then this allows data analysis tools like MapReduce or Spark or anything within the Hadoop ecosystem. There's a vast array of technologies all within the Hadoop ecosystem that work with Hadoop to then do data analysis on. So it's worth mentioning that Hadoop is really only one side of the coin. You do need something else to actually search and ask your data questions. All right, so how does it work? So we have a name node here. That's essentially the master node. And the name node keeps track of the cluster, keeps track of all the data nodes, and it keeps a file registry. It knows where all the files are on each of the nodes and how they're broken up. So files are broken up into blocks. So in this case, we have some file here, some file.txt. We're going to break it up into two blocks, block 1 and block 2. And then we're going to write block 1 to data node 1 and data node 2. We're going to write block 2 to data node 1 and data node 3. So now we have basically this file exists with one degree of replication. So we have the initial copy and then a replica copy. And we've also segmented this file into smaller pieces so that we can spread it out. So we have full fault tolerance here. If we lose data node 1, which has block 1 and 2, it has a full copy of the file. Data node 2 and 3 together have another copy of that file. So you can kind of see the similarities here to what we were talking about in the architecture section. Blocks in this case is what we were calling, chunks before. Name node is a master node. Data nodes are just the worker nodes. And the master node or name node here is essentially keeping track of all the nodes in the cluster and keeping track of all the files, how they're broken up, where those pieces of the files are throughout the cluster, and what degree of replication they have. So hopefully this looks really familiar to you. All right, so that's just a quick overview of Hadoop, HDFS. This is probably the most ubiquitous technology we're going to talk about in this section. Because it was one of the early technologies, one of the most popular technologies, it grabbed a lot of market share, and it has been waning a little bit in popularity just because of the newer, better technologies out there. But Hadoop is still very much a major player in the big data industry. So we talked about one of the earliest distributed data storage technologies for big data. Now let's talk about one of the earliest data analysis technologies that was built on top of HDFS, MapReduce. So MapReduce is a processing technique that maps a set of data by filtering or sorting and then reducing each set into a summary. The summary can be counting, averaging, searching, whatever the question being asked of the data is. So MapReduce jobs are written in Java, And MapReduce primarily operates on top of HDFS, but it has been adapted for other distributed file systems as well. Now, as you can imagine, because this is a big data technology, the MapReduce operations are very horizontally scalable. So instead of asking a question to a big mountain of data, we can ask a question to that mountain broken up into dozens, hundreds, or even thousands of smaller pieces. You ask all of those pieces the same question at the same time, and you get an answer back exponentially quicker. So as we mentioned, it's used to analyze data on a distributed file system. It's used for sorting, searching, doing graph analysis, and statistical analysis on very large data sets. And it also has a lot of machine learning applications as well. So let's take a look at how it works. So this is a very, very simplified, very high-level overview of how MapReduce actually works. And it's been colorized to kind of help see what's going on. To really understand how it works at a low level, we'd have to dig into some Java code. So this is just a very simplified graphical representation of what MapReduce does. And there's actually more stages than just map and reduce, which isn't represented here. And the number of stages there are can depend on what your specific Java application is doing. But generally, this is how MapReduce works. So we have an input. So an input is some distributed file system in this case. In this case, we have 5 nodes. That could be 100 nodes or 1,000 nodes. We have data spread out across all of these nodes, and we want to basically ask the data some questions. So the question can be just about anything, but ultimately what we have to do is we have to ask that question to every single node. Then we have to sort the answers from each node and then reduce those answers down. So when we ask that question to each node, that's essentially the mapping here. So we have some answers coming out of each of these nodes. Now we need to sort this data. So you can see the red block here kind of indicating the answer of some question is being all sorted over here, green here, and blue here. And then we can reduce this answer down into the final output. We can see how we can take a question and ask it to a massive volume of data, but it's broken up into smaller chunks. So now we can ask each chunk, we get an answer, we can sort all the answers from all the chunks, and then we can reduce the final sorting down into the final answer. So you can see how this can become extremely horizontally scalable. You just keep adding more and more nodes, and you can ask bigger and bigger data sets questions. So just like HDFS, there are other technologies kind of taking the place of MapReduce, more modern technologies. But again, MapReduce was really, really popular really early on, so it grabbed a big market share, and it still is also a major player in data analysis within the big data industry today. All right, so let's talk about one of the more modern technologies that has kind of come into the scene more recently and is a bit of an adaptation of MapReduce and HDFS and those types of technologies, and just takes it a step further. So let's look at Spark. So Spark is a general purpose cluster computing framework designed for big data. So that is a fairly ambiguous definition. That's because its use cases and its functions is somewhat ambiguous as well. It is extremely adaptable and flexible for just about anything you needed to do in terms of cluster computing, which is to say performing a job across many, many compute nodes. So breaking a job up into small subtasks, spreading it out across a bunch of compute nodes, and then coming back with the answers. So that sort of architecture of asking data big questions distributed across multiple nodes is perfect for a cluster computing framework. It is an Apache open source project, so it is heavily worked on by a lot of people all the time, so it's always improving. And because it's open source, it's also very, very adaptable and is able to work with a lot of other technologies. Now, one of the really popular abilities of Spark within the industry is its capability of in-memory data processing. So we'll talk a little bit more about how it works. But you can essentially see here over on the worker nodes, we have a cache. So Spark is actually able to, if you configure it properly, if you configure it with the right nodes with enough memory in them, you can actually load your entire data set, your entire distributed data set, into a computer's memory, or RAM. Now, for those familiar with computer architecture, RAM is exponentially faster than disk. RAM is very highly optimized for read-writes, and it's very close to the CPU, so it's quickly accessed and has a lot of bandwidth between itself and the CPU. So the ability to load your entire data set into RAM will tremendously impact the speed at which you can analyze your data. Cannot emphasize this enough. In-memory data processing is kind of the holy grail of data analysis performance. So Spark was very much engineered with performance in mind. So unsurprisingly, because it's an open source project, again, it's very flexible, so it has a lot of really easy to use APIs, very extensible, and it works with a ton of other technologies. So I just have a couple listed here because these are the technologies we're talking about in this section, but it works with HDFS, Elasticsearch, Kafka, MongoDB, and plenty more. In fact, it kind of got its foot in the door because of how easily it works with HDFS. You can actually deploy these worker nodes to your HDFS data nodes and essentially treat them as worker/data nodes. So you have your name nodes kind of managing your HDFS data nodes, and then you have this cluster manager here managing your Spark worker nodes. But the worker nodes and the data nodes are the same thing. So now you have this distributed data, and you have the worker nodes on each of those nodes, and you can really start to leverage Spark on top of HDFS very easily. So what is it used for? So it's used for very fast data analytics. Again, it's engineered with performance in mind. We'll talk a little bit more about that when we get to how it works, but it's used for data analytics. So machine learning, graph analysis, and then also data streaming. So data streaming is live data processing. Data is being created, and from the point it's created, you want it collected, processed, stored, and analyzed in as short amount of time as humanly possible. And because Spark is so fast and engineered with performance in mind, it is perfect for streaming applications. All right, so how does it work? So there are a few variations to Spark architecture. So this is just a very simplified overview of a small-scale distributed deployment of Spark. So we start with the driver. So the driver is essentially the job. So this is the code. This is what's asking the questions. The driver operates through a cluster manager in a distributed mode. You need some sort of manager. In this case, this would be their version of the master node that keeps track of all the worker nodes. Ask that question to the cluster manager. The cluster manager then sends that question to the corresponding worker nodes. The worker nodes are sitting on top of some kind of storage, or it's sitting on top of HDFS or Elasticsearch nodes, or whatever you happen to be using for data storage. So the worker has a built-in cache, which is great for frequently asked questions. So particularly for data streaming, let's say you have operational analytics use case, so you have a dashboard up showing, response times for your website. Maybe you're refreshing that dashboard every second. Well, if you're asking that question every second over and over again, well, these worker nodes can just cache the answer so that it can respond very quickly. Again, this is engineered with performance in mind. So having a built-in cache into each worker, whether or not you're doing full in-memory or not, you still have some level of in-memory cache to help speed up your data analysis. So the other component of the worker here is the executor. That is the part that actually performs the subtasks. So the executor performs these subtasks, it'll cache it if necessary, and then return the answers back to the driver. And then now just to scale out your cluster computing, you would just add more and more worker nodes as necessary to handle larger data sets or to get faster answers to your questions. So this is just a quick overview of Spark, very high performance data analysis tool, extremely flexible, very easy to use to get up and running with a lot of built-in APIs that kind of help hold your hand and get things plugged in and working very quickly. And it works with a ton of other technologies. So whatever your architecture looks like, there is surely a way to make Spark work within it. So we've talked about a data storage technology, HDFS, and we've talked about MapReduce and Spark, which are great use cases for data analysis technologies. So the next one we're going to talk about is a newer technology as well called Elasticsearch. And what sets this apart from what we've talked about so far is that it is both a data storage and a data analysis technology. So it is a distributed search and analytics engine, which also stores the data it's searching and analyzing. It is highly fault tolerant and very much horizontally scalable, as the name implies, Elasticsearch, and it is designed to be very fast. So what is it used for? So it's used for really fast search, as again the name would imply. It's elastic, so it's horizontally scalable, and search, used for search. So it's great for search engines, for product search, for whatever your search needs are. It's great for NoSQL databases. So everything it stores is in JSON format and semi-structured format. So it is great for application backends, database backends that want to leverage NoSQL. It's also really good for machine learning. And in fact, it has a lot of machine learning features built right in for doing statistical anomaly detection and even some predictive analysis. It's really great for data analytics. It has a lot of built-in search and aggregation ability. So it doesn't just store the data, but it's also able to aggregate it and answer really complex questions about the data it's storing. And lastly here I have logging. So Elasticsearch kind of became popularized in the use case of log aggregation. So in conjunction with some other technologies within the Elasticsearch ecosystem, it made a really good search and analytics and storage tool in a log aggregation pipeline. So let's take a look at how it works. So we have a master node. So in this case, we have 3 master nodes. So the master level of nodes is clusterable in Elasticsearch. So they're actually called master eligible nodes. And then the actual elected master node is the master node. The master node basically manages all of the data nodes. So in this case, we just have 3 data nodes. So Elasticsearch stores data in indexes. So if we were to try to compare this to a traditional database, an index would essentially be a table. So each index is basically a collection of documents. These documents are spread out into shards. So in this case, we have an index made up of 3 shards. Let's say it had 1 million documents in this index. So a third of those million would be in primary shard 1, primary shard 2, and primary shard 3. So if you want to search all 1 million documents, we can just search from all 3 shards at the same time and get 3 times the speed versus searching all million at the same time in a single node. But we can also use sharding for replication. So you can see down here at index 2, we have primary shard 1, then we have replica shard 1 and replica shard 1 on the 3rd node as well. So you can combine both sharding for performance and for replication. So if I had maybe 25 nodes, I can have an index comprised of 5 shards and then maybe 3 degrees of replication. So that would be 20 shards in total, which would evenly spread out across my 25 nodes. So I have both a high degree of fault tolerance and a fair amount of speed because my data is split out amongst multiple nodes. And Elasticsearch is great for very high variability data, so data that's very distinct and it's not all the same. You can kind of lump data into indexes. So let's say I'm using this for log aggregation. So maybe I do an index per application because sometimes an application is going to log a bit differently. The data is going to look a little bit different. It's going to be stored a little bit different. So maybe I just do an index per application. That way I kind of have a nice category of data stored in my cluster. It's not just all there in one big lump. So again, Elasticsearch is really the only tool that we're talking about here in this section that is a true, fully distributed data storage technology with redundancy and fault tolerance and speed built in, and also a very comprehensive data analytics tool. It can do advanced analytics, it can do pipeline aggregations, it can ask its own data questions and provide answers without having to use other tools. Now, with that said, it is part of an ecosystem of tools. So Elastic, the company who owns Elasticsearch, also has other tools. One of them in particular named Kibana actually plugs right into Elasticsearch and allows you to visualize the analysis that Elasticsearch can do. So Kibana itself doesn't actually do any real analysis, but it can visualize what Elasticsearch does. So it allows you to create these graphs, these charts, these dashboards, reports. You can visualize your machine learning algorithms and really get that visual representation in a web browser of what Elasticsearch is doing in the back end. So again, Elasticsearch is a super flexible big data technology. Whether it's big data, whether it's small data, it can scale to your needs. And depending on your use case, it can scale to that as well, whether it's for searching, for NoSQL database, analytics, or log aggregation. Elasticsearch is certainly elastic enough to fit whatever your needs are. So next we're going to talk about a data streaming application or data streaming technology called Kafka. So what makes this different from the rest of the technologies we talked about here is that this is a data storage technology for particularly streaming. So what that means is as data is produced, it is kept in its order. It's kept in order in which it was produced. So in the chronological order, as data comes into these topics, which we'll talk more about this architecture in a minute, all the data is kept in a very specific order so that it can then be consumed in that same order. Whereas with Elasticsearch and with HDFS, we're just kind of storing data in no particular order. We're just kind of spreading it out and then searching it as we need to. But Kafka is a bit different. We're not just storing it for the sake of searching it. We're storing it for the sake of consuming it, specifically consuming it in the same order in which it was produced. So Kafka is a distributed data streaming platform. Distributed meaning we are storing the data amongst and across many, many nodes. It is a multi-tenant publish and subscribe capability, like a message queue. So you can see here we have multiple producers via these producer groups, and we even have multiple producers within a single group. The same thing for the consumers as well. So it's multi-tenant. It stores streams of data with replication. So these are data streams kept in order. We can also replicate them, as you can see here with topic 2, with partition replication. And as I said, it is a real-time stream processor. So what is it used for? So this is a great use case for data pipeline buffers. So if that sounds familiar to you, if we go back to architecture, data ingestion here, this queue that we talked about earlier, where all the data comes in from all these different sources, you want to ultimately end up into a queue to use as a buffer for back pressure and for downtime. So if you look at all of these different data sources here, they're all very, very different. The data is going to look very different. And once it's in the queue, you can have multiple things consume this data. In this case, we just have a data processor consuming it. You can have another application, a dashboarding application, whatever it might be. In your data ingestion pipelines, it's very common to have a multi-tenant publish and subscribe queue. This is exactly what Kafka is. So heading back to technologies here, it can also be used as a data pipeline distributor because it is a multi-subscribe. So again, we get data from all these different locations, and we don't just want to share that data with one application, we want to share it with other applications. So what that means is using consumer groups, again, all this data is stored in order. So if I store 10 documents in topic 1, and they're stored in orders 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, consumer group can read 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in that exact order. And it can be split between these two consumers because this is a consumer group. So maybe this consumer reads document 1, this reads 2. Now we can use a completely separate consumer group, which has its own offset. So the offset here is at 10 because that's the document that it has read up to. So once the 11th document comes in the topic 1, boom, this is going to read document 11. But consumer group 2 can now subscribe to this topic, and it can start all the way back at 1 and could read all the way up to 10. And same with consumer group 3. It can start at 1 and read all the way up to 10 because it's a separate consumer group with its own offset. And you can also have a consumer group like here with group 3 that subscribes to multiple topics at the same time. So there's a lot of flexibility here. You can have multiple things produce, you can have multiple things consume with their own individual offsets, and then also within a consumer group, you can have multiple consumers that share an offset to help you consume the data faster. So if the consumer can't keep up with a producer, then you just add more consumers to your consumer group. They all share the same offset and then can therefore consume the data at a faster rate. So this is great for building real-time data stream applications that have to react to streams of data. So these consumers over here need to react immediately. Maybe there's some kind of application, dashboarding application, or there's some kind of application that takes an input and immediately produces some sort of reaction to that input. So you want these things to react instantaneously to when data is created. So these producer groups will create the data, throw it into a topic, and then they can be consumed immediately. And Kafka can also be used as a message queue, which is similar to a data streaming application. It's just that message queues aren't necessarily always real time in terms of consuming. All right, so how does it work? So we've talked a little bit about how it works already, but essentially we have Kafka nodes, and we have topics and partitions. So this looks a lot like what we just talked about with Elasticsearch. So if we jump back here, we have data nodes, we have indexes. Indexes are spread out across the data nodes using shards. Shards can be used to break the data up, and they can also be used to replicate the data. So it's very, very similar here with Kafka. We have Kafka nodes, we have topics, and then we use partitions to spread those topics out across multiple nodes. And we also use partitions to replicate the topics across the nodes as well. So again, if I had 20 Kafka nodes, I had a topic with 5 partitions, I can replicate that partition 3 times. So I have 20 total partitions spread out across my 20 Kafka nodes and get both the speed and fault tolerance benefits of spreading this data out across a distributed cluster. Now the cluster management you'll notice is missing from this diagram. Kafka actually doesn't use a cluster management by default kind of built in. It uses something called Zookeeper, which is an open source cluster management, kind of general purpose cluster management technology. And that does all of the cluster management that we've talked about in the other technologies. So Elasticsearch has its own master nodes. HDFS has the name nodes. So Kafka uses Zookeeper to essentially orchestrate these Kafka nodes. All right, so getting data in, we've covered this a little bit. But you can have multiple producer groups, as many as you want, because it is multi-tenant. Within each group, you can have multiple producers, and the same goes for consumers. So you can have individual consumer groups, all with their own offsets, reading the data at their own rate, at their own speed. And then you can also have multiple consumers within a single consumer group that share an offset to read the data at a faster rate and to kind of split the load of the processing. So Kafka is a fairly integral component to a lot of big data pipeline technologies. Whenever you're dealing with big data, you're typically not working with a single technology. So as we talked about back in the architecture here, we're not working with one technology here, right? So we have a data storage and analytics tool. Sometimes you have multiples of these. You don't have just one. You might have a reporting tool. You might have an analytics tool. You might have a machine learning tool, but they all need to feed off of relatively sometimes the same data. So you need that multi-tenant publish and subscribe technology to kind of sit in here to both disperse the data to all your different tools and to also provide this buffer and this fault tolerance for back pressure and failure. So Kafka, as you can see, is a perfect candidate for that use case. So it is no wonder why Kafka is so frequently used in big data stacks and big data pipelines, and is therefore very popular within the big data industry. All right, so we've covered various technologies in this section. So we talked about standalone storage, analysis, combination storage and analysis, and then also a streaming technology here. So now we're going to talk about a NoSQL database. So MongoDB is through and through a NoSQL database. So this is a distributed document-based NoSQL database that stores data in JSON-like documents. So as we know, NoSQL databases are semi-structured. JSON is a semi-structured format. So NoSQL databases are document-based instead of row and column or table-based. And this is fully distributed, so it is able to scale horizontally and handle very, very large data sets, such as big data. And along with being distributed, it can also handle data replication as well, so that it can be highly fault tolerant. So what is it used for? Just NoSQL database. There's not really a whole lot of other use cases out there from MongoDB. That's what it was built for, and that's what it's really, really good at. All right, so how does this work? So we have basically two main services here that runs. We have MongoS and MongoD. MongoS is basically the router, which is essentially the cluster management of the Mongo cluster. And then we have these MongoD servers. So we have replica sets. So this is how we spread the data out horizontally throughout replica sets. And then within each replica set, we have a MongoD server, at least one MongoD server, that contains the actual what's called the replica, or the chunk of data. So within each replica set, we have replica 0, 1, and 2. We can add more and more nodes to increase that replica count for higher fault tolerance. Then we can add replica sets to increase the amount of nodes we're spreading the data out across for read and write performance. It's fairly simple how it works, and what it does is very focused and targeted. It's a very, very good NoSQL database. It doesn't try to be a lot of other things. The other NoSQL database we kind of talked about here was Elasticsearch. It's used for quite a number of different things between search and machine learning, data analytics, and also it can be used as a NoSQL database because, again, everything is stored as JSON documents. So it still has that semi-structured storage and scalability. So both of these technologies can perform that NoSQL database role. The only difference being that MongoDB is a little bit more targeted as a NoSQL database. It does have some data analytics capability, and being a database that has quite a bit of search capability. But what it does really well is ultimately what it was designed for, and that is a NoSQL database. Next, we'll take a look at how big data is used in the education industry. So something that I have personal experience with is with career planning. I actually took a career planning exam when I was in college to help figure out where my competencies were, to figure out where my interests were, and then correlate that to potential career paths. So with big data and questionnaires, we can help determine optimal careers for individuals based on both their competency and interests. This goes back to that kind of correlation analysis between, people who are really good with X might enjoy doing Y, or people who enjoy doing Y would excel really well at career Z. So kind of combining psychology with machine learning and correlation analysis, we can figure these things out. Something else I'm familiar with, because I worked at a higher education institution, I worked at a university, is student success. And there, the business intelligence office was working on ways to identify at-risk students, or students who exhibited, unusual turn in academic performance. Maybe they stopped showing up for classes. Maybe they're a straight A student and they started getting some C's and D's. Maybe they failed a class. And this was a way for us to kind of identify these changes in behavior, these changes in patterns, and reach out to these students. So then we would have a student advocate or the registrars or someone reach out and just check on them, make sure everything's going okay, and how they can help make that student more successful. Another use case here, again, one I'm familiar with, is cheat detection. I know that when I was in college, pretty much every paper I ever wrote went through some sort of plagiarism analysis tool to detect whether or not I copied someone else's works. So plagiarism can be easily detected by comparing student submissions with what's available on the internet or various publications. And this analysis kind of goes a little bit further than just seeing whether you use the same words as something. Even if you go and, you read an article and you just kind of paraphrase that article, some of these cheat detection algorithms are really advanced, and they can see those synonyms between the two, and they can see that you're saying the same general thing just with different words in the same flow and the same pattern as something else. So these algorithms are able to detect that and then inform disciplinary decision making. Now that we have a good idea of the terminology, the architecture, and some popular technologies in big data, let's take a look at some use cases. So we'll head over to use cases here. So I'm going to break these up into different sections. So first here we have the Internet of Things, or IoT. So we talked a little bit about IoT in the architecture section, as IoT is one of the biggest sources of data we have. And again, IoT is a massive umbrella of internet-connected devices, or Internet of Things. So the two biggest categories of IoT devices that we have are sensors and smart devices. So sensors could be sensors in your vehicle, weather sensors, geological earthquake sensors, various types of geology sensors like soil sensors, anything that has an RFID chip, which these days is just about everything, whether it's your package that you're getting delivered, ID cards for security access control. All of these little sensors embedded all over the place are automatically generating data without really any human intervention. There's just massive amounts of data being generated through the use of these sensors and through the continuous monitoring that these sensors provide. And then the other category here is smart devices. So I feel like every week or even every day, something that was, just a normal appliance or whatever is now a smart appliance. So, I mean, they have smart refrigerators and toasters nowadays that connect to the internet. But smart devices can be anything from thermostats, cameras, your TVs, your appliances, any home automation device. So, carbon monoxide and smoke detectors, doorbells, any device that you have that's connected to the internet that's not a phone or a computer. So again, IoT devices is an ever-growing category of data sources that is just constantly spewing out huge amounts of data. And to some people, that data is extremely valuable. There's a lot of insights they can gain from the usage of these sensors and from the usage of these smart devices. Continuing on with our use cases, next we're going to look at e-commerce. So whether you realize it or not, the big data industry is having a huge impact on your experience whenever you're shopping online. So let's take a look at some of these categories here. So we have the recommendation engine. So a recommendation engine basically takes all of the sales data of things you've purchased, of things other people have purchased, and creates a relational graph between those purchases. So it creates a relational graph between the item that you bought, or an item you bought, and the items bought by other purchasers who also bought that same item. So if I buy item A, and then someone else buys item A, B, and C, the recommendation engine might recommend to me items B and C. So this is a very effective and easy way to focus target advertising of specific items or products to someone based on their interests compared to the interests of other shoppers. Another big use case is to predict shopping patterns. So what items sell, when they sell, how much they sell at given times of the year is not usually a very easy to understand or a very predictable thing. But by using historical sales data, we can essentially predict what items are going to sell, how many of them, and when. Now that gives the business owners the information they need to stock up on the right items so that their inventory is always just right. They don't have too few items so that they're constantly selling out and missing out on potential sales. They don't have so many that they're using up a bunch of space in inventory. So predicting shopping patterns is a great way to optimize e-commerce inventory. Another use case that I'm sure we're all familiar with is product search. So if you ever go online and you search for a particular product, oftentimes you're adding a bunch of filters, things that you can check off on like a sidebar, like the positivity of the reviews, the brand, the price range. You're searching for some keywords. All these things are applying search filters that is searching a massive library of products. And the thing with search that's kind of a little bit different than a lot of other big data use cases is that search is heavily optimized for read performance. Because if you imagine having a product library, that product library is not growing by tens of thousands of products per minute or per second. So you don't have this high velocity of data coming in. You don't really need a ton of storage per se, or a ton of write ability. What you want is for searches to happen very quickly, because that is user facing, and users get very frustrated when they type in a search term and it takes a long time to get a response. So very fast rapid search here. So spreading that data out across a whole bunch of nodes to get those searches back as fast as humanly possible. So we talked about using big learning to predict shopping patterns to help with managing your inventory, but then you also have another aspect of managing your inventory, which is just keeping track of what you have and where it is, and then comparing that to what you need. So managing the inventory and predicting the shopping patterns are kind of two sides of the same coin. I have to know what products I have, where they are, spread out all across the globe, maybe hundreds or thousands of warehouses. And I have to know for each warehouse how much of a particular product I need versus what I have. Because again, predictive shopping patterns, those could be time-based, product-based, and also geographically based. Things are going to sell better in certain parts of a country or the world than others. And it's those types of insights that we're really trying to glean from this information, from this big data, to better the e-commerce experience. All right, so let's take a look at how big data is used in the healthcare industry. So first we have electronic health records. So historically, health records have always been paper, so hard copies. So you see, those big filing cabinets, those rolling filing cabinets and collapsing filing cabinets to store these thousands and thousands and thousands of health records at a particular medical facility. It then becomes very difficult to share those health records with other medical institutions. So let's say you change doctors, they have to scan and fax all that medical history. But by digitizing our health records and storing them electronically, you can have all of that health information, so the demographics, the medical history, allergies, test results, etc., all stored electronically. You can store that redundantly using the concepts we talked about in the architecture section. So that data is always highly available, and that also allows you to share it easily with other institutions. Another producer of big data is medical devices. So whether it's a device used in a hospital or a wearable device, maybe it's a smartwatch, an activity sensor, maybe you have something monitoring your blood sugar, or maybe you have, a pacemaker or something inside of your body. Medical devices create a lot of high value data. So again, one of the biggest use cases of big data is to dig massive amounts of data to glean insights from that data and then inform critical decision making. Well, what more critical of a decision could you make than something about your health, something about your life? So these medical devices are creating extremely high value data, making it very important to collect and analyze this data to make informed decisions upon. Another use case here is staffing. So it's really hard to staff medical institutions properly. My wife is a nurse, so she knows this very well. Sometimes she's working on the floor and there's not enough nurses. There's way too many patients. They have too many patients to a nurse and they're just too busy. Other times they have too many nurses and there's not enough patients to keep everyone busy. So staffing is a really important problem because too many workers will increase healthcare costs, whereas too few workers can lead to bad patient care. So using predictive analysis and historical medical data, we can kind of predict what our staffing needs are based on maybe the floor in the hospital, so the ER versus oncology versus the OR, the time of year. So I know holidays, there's a lot of ER visits. Thanksgiving, people are hurting themselves deep frying turkeys, and Christmas, people are falling off roofs, putting up lights. So kind of gleaning these insights from hospital records allows us to make more intelligent staffing decisions. And then lastly, we have medical treatment. So data mining health records, doing machine learning and deep learning on these health records, we can kind of create these correlations between things. So we can figure things out like, for whatever reason, people who do X have a 50% less chance of getting Y, some disease or illness. We can find these correlations. Basically, we can use data science to find these questions that we didn't even know to ask. We're like, why does this happen? We didn't know this correlation existed. Why does this exist? Now let's use data analysis. Let's use medical science and biology to figure out why that happens that way. So data science and data mining to help with medical treatment and to help with medical correlations between diseases and human behavior is an extremely important and very quickly growing use case, as I'm sure you can see why, in the healthcare industry. Last but certainly not least here I have for use cases is information technology. And again, I just want to say that these are just a few of the kind of areas in which big data is used. Obviously, there's way more industries, way more categories you can think of. And then within each of these categories, there's obviously way more use cases as well. So I am just providing a very high level, kind of low-hanging fruit overview of some of these use cases. So here we have information technology. So the two biggest use cases that I see here and I have personal experience with is operational analytics and monitoring. And they kind of go hand in hand. They're really two sides of the same coin. So operational analytics is log and metric aggregation. So this can be from your application logs, your web server logs, your networking devices, end user devices, client devices, those types of things. In a large enough company, you're looking at tens of thousands or even hundreds of thousands of events per second coming into an operational analytics pipeline. And then you ultimately would use that information to troubleshoot issues with your infrastructure or with end user clients. Or by using machine learning, you can help predict issues before they happen. So if a particular issue has happened, a bunch of times with machine learning algorithms, it can know the circumstances around that issue, and it can begin to look for those circumstances. And if it starts to detect those circumstances, then it can say, hey, this issue is likely to occur with this device or with this user. It's also a great way to do security analysis or a SIM environment. If I have a particular user logging in from multiple IPs that are geographically spread out across the globe in a short amount of time, I know that someone is trying to use this user's account without their permission. Or if there's a sudden egress of data from a particular part of my network, it's likely someone is exfiltrating data out of my company. So by collecting all this data into an operational analytics pipeline, using machine learning and other analysis techniques, we can increase uptime and we can decrease incident time, or the time to resolution for incidents. So again, the other side of the same coin is for monitoring. So using machine learning to find anomalous behavior in your systems and services, to either quickly react to anomalous behavior or to help predict anomalous behavior. Ultimately, the goal here is to monitor everything as much as possible so you can react as quickly as possible to any issues, either when they happen or ideally before they happen. Let's take a look at how big data is used in the finance industry. So something that you may have experienced, or maybe you haven't, but it is happening in the background whether you realize it or not, is fraud detection. So by familiarizing themselves with your spending habits, algorithms, machine learning algorithms, can detect unusual spending and even prevent unauthorized purchases. So this is kind of similar to like statistical anomaly detection. Basically, an algorithm is learning your patterns, learning the things that you buy, where you buy them from, what time you buy things, and geographic locations from where you buy things. And it kind of establishes this pattern. So every purchase now has a probability of you making that purchase. And as long as the probability of you making that purchase is very high, then everything's good. But as soon as a purchase is made that falls outside of high probability, so it's a very low probability purchase, maybe it's in a foreign country, maybe it's, in a foreign country in the middle of the night from somewhere you've never shopped before, or something was purchased that you just never would have bought for yourself. These fraud detection algorithms can either alert depending on the probability of that. So if it's not a super low probability, and maybe it just alerts you and it asks you, hey, did you buy this stuff? Or if it's super anomalous, it's extremely low probability of you purchasing something. Maybe it's a very, very large amount at a weird time at a weird location. It could just block the purchase altogether. Another use case here is for trading. So using statistical models and advanced algorithms, computers can actually trade faster and way more precise than any human. It's actually kind of scary how quickly computers can make decisions in terms of making these financial trades on the stock market and creating these kind of micro trades that make these small gains over and over and over again that turn into big gains over time. So there's a lot of algorithms, there's a lot of data being used in the trading industry. And in fact, a lot of the extremely fast data analysis technologies that we have in the big data industry were spawned out of a need for financial trading, because it has to happen at lightning speed. Things have to be extremely quick. So clusters of big data infrastructure that is specifically designed for extremely high performance is usually used in these types of trading environments. So next we have credit scoring. So credit scoring is essentially just a risk assessment. So credit institutions calculate the financial risk of lending money to an individual based on financial history and even behavior and life choices. So there's a degree of correlation analysis here as well. Credit companies with their vast amounts of data can make these correlations between their historically bad borrowers, people who defaulted on their loans or whatever it might be. They can analyze their behavior. They can analyze various things about their financial history, and they can correlate that to future borrowers. So they know that 60% of people who default on their loans do X. So now we know before we lend money to a new borrower, we should see if they fall into that category as well. If they do, then we're going to increase the risk of lending money to them, which will ultimately have an impact on whether you're accepted or not. And if you are, then it might have an impact on your interest rate. So similarly to credit scoring, insurance companies kind of do something very similar, with underwriting you. So underwriting is the process to basically measure the risk and determine your premiums based on the risk. So if I'm an avid mountain climber, then maybe my life insurance premiums are a bit higher because I'm at high risk for injury or death, but my health insurance injuries might be a bit lower because I'm very active and healthy and fit. So again, by having this historical data, this health information, these life choices information, these insurance companies can make these correlations between people who are very costly and people who weren't very costly, and then use that information to underwrite future clients, and then more accurately determine their monthly premiums. Next, let's have a look at how big data is used for business intelligence. So business intelligence is often a department within a given company that uses data, uses information to inform critical decision-making about their company. So use case here, number one, is for marketing. So by analyzing customer behavior and sales, businesses can more accurately measure the effectiveness of a marketing campaign. So we talked about this a little bit back when we were talking about machine learning here, by doing success rate measurements. So we can use machine learning algorithms to measure the success of a marketing campaign, for instance. That tells a company whether or not they need to keep spending, thousands or millions, whatever it is, into a particular campaign, or to just cut their losses and take a different route. So it's always important to know as a company whether or not your marketing is paying off, whether you're getting that return on investment. So another use case, and sometimes unfortunate use case, is cost cutting. So analyzing company expenditures, and you can then expose ways of cutting costs. So it could be as simple as buying cheaper coffee for all the break rooms, or it could be as extreme as laying off a bunch of positions because it turns out there's a much more efficient way to staff a department that requires less people. So sometimes this isn't always in the best interest of the individual, but it is usually in the best interest of a given company, as it does allow them to cut costs significantly and increase their bottom line. Another use case within business intelligence for big data is to find high value targets. So high value would be the ratio of value to cost, or low-hanging fruit, we might call it. So determine ways to boost productivity or sales with the lowest cost or risk, but with the highest relational value. So big data is a great way to kind of find these insights within your company's behavior, within their expenditures. Maybe you have customers or clients going out of their way to do something a certain way that you don't really support out of the box, and you can create avenues for which they can do that more easily. Or maybe you're losing potential clients and customers because of some small little thing that you didn't know about. These are the types of insights you can discover when you start gaining insights from your business data. And then lastly here is just asking ad hoc questions. So you have all this data about your business, about your sales, about your employees, about your products, whatever it might be, and someone needs to make a decision about something and they're not entirely sure what to do. Oftentimes there is a supporting argument to a specific answer to those questions hidden in your data. So asking ad hoc business questions is probably the most common use case of business intelligence and big data in business intelligence, because a lot of times you need help making a decision and you want to back that with data, or you've already made a decision and you want to help justify it with the data you already have. So before we take a look at what's next, I first want to congratulate you on completing this course. I hope you found this course illuminating and informative on what big data is, why it's necessary, and at a high level how it works. So let's take a look at some other courses that you might be interested in. So I broke this up into difficulty tiers. So first we have the beginner courses. So database essentials. We talked a lot about traditional databases in this course as an effort to compare and contrast them to big data. So traditional databases are still very relevant and very applicable to quite a few use cases out there. So I would definitely take a look at the database essentials course. We have another one of my courses, which is a Hadoop quick start. So this is just a very beginner level introduction to Hadoop and MapReduce. And then we have a lab and some demonstration videos that help you get running with HDFS and MapReduce very, very quickly. Another one of my courses is the Elasticstack Essentials. So the Elasticstack is the Elasticsearch ecosystem. So there's other tools within the Elasticstack that work with Elasticsearch. So there's a bunch of Beat clients. There's, I think, like 10 of them now. There's Logstash, which is the data processor, Elasticsearch, which is the storage and analytics engine, and then there's also Kibana, which is the web-based analytics tool that visualizes all of the analysis that Elasticsearch does. So the Elasticstack Essentials kind of gets us up and running very quickly with all of these tools and allows you to create a data collection pipeline for some system logs. Next, we have the Big Data Essentials, which is similar to the one you just took here with the Big Data Fundamentals. It's just a little bit bigger of a course and a little bit more in depth. For intermediate courses, the first one here is one of my courses, the Splunk Deep Dive. So Splunk is essentially one of the competitors to the Elastic Stack. So they're primarily used for log aggregation and security SIEM environments. So the Splunk Deep Dive is just a very quick introduction to Splunk and has a bunch of labs to help get you up and running with it and secure it and using it to analyze some files. Next, we have the Elasticsearch Deep Dive. So this is a very hands-on, demonstration-heavy, lab-heavy course that we get a lot deeper into Elasticsearch from an administrative perspective. So how we deploy it, how we manage it, configure it, how we get data in and search the data and access it. Then we talk also a lot about how to size it correctly, depending on your use case. So the last intermediate course I have here is the Azure exam for the DP200. Implementing an Azure data solution. So this will prepare you for that exam. So moving into the advanced section here, these are all certification preparation courses. So each one of these courses will prepare you for the requisite certification. So we have the AWS Machine Learning, the Google Cloud Data Engineer. We have a Elastic Certified Engineer preparation course, which is the certification for Elasticsearch. And we have the AWS Certified Big Data. So if you found the content of this course interesting and you want to learn more about big data, these are definitely the options that I would suggest you look at, starting with beginner and working your way up to the advanced courses. And as you get into the more advanced courses, you're starting to work with certification preparation courses, which at that point you're ready to start taking and passing some certifications. So I just want to thank you again for taking this course and providing any feedback you may have provided. I definitely review all the feedback as it does significantly impact how I do courses in the future. And a common question I get sometimes in the feedback is, what other courses have I done? So just from this list here, I have the Hadoop Quick Start, the Elastic Stack Essentials, Splunk Deep Dive, Elasticsearch Deep Dive, and the Linux Academy's Elastic Certification Preparation course. So if you enjoyed the things we talk about in this course, then definitely check out one of these other courses here to take your data knowledge to the next level.